And what I don't want to do is create a quiz today and only give you 3 days to complete it. I figure if I'm engineering, as we've all agreed upon, we'll have 1 week that's sort of dedicated to just soils and soil mechanics, and then another week that's dedicated to foundation. Still getting the appropriate amount of time. And plus, it's not delaying the today. As you all are aware, I've been recording structural on reinforced concrete design, structural steel design, but actually I was going from a lecture I did about 1.5 years ago. So what I think I'm going to do is you should be good. Now that video does cover the videos are there, or the videos there. I'm going to just sort of splice that in at the end of this introduction and let that serve as the review for this week. So if that's all, I will see you all. All right, so we're back and we're going to talk a little bit about structural design. Now, just a heads up, the structural design portion of the FE is only going to cover 2 main topics, one being steel design and the other being reinforced concrete design. So what we're going to cover tonight is each topic one at a time. We're going to start off with reinforced concrete design, and I'm specifically going to focus on beams and columns. Beam analysis and design for moment, beam analysis and design for shear, and then columns. Okay? Now steel design, I'm going to do columns, beams, and then I'm going to do tension members as well. One of the ways I wanted to organize this is I wanted to do the concrete stuff first, because here at Marshall you are required to take reinforced concrete design. Steel is an elective. So I know some folks in this room have not had steel design. That's okay. I'll do my best to try and gloss over the big stuff. If you haven't had steel design and you get a steel design problem on the test, I mean, you can take a stab at it, but really if you haven't been exposed to the material, it might be a guess see and move on category. That's okay. It's not very many questions. You know, we talked about this last time. This comes from the end of the FE reference manual, and it discusses the exam specifications, what topics are going to be covered, how many questions you are to expect. And if you notice, for structural design, design of steel components, design of reinforced concrete components, and you're looking at 6 to 9 questions. Okay. Now, I want to take you through some of the stuff that you're going to get in your get in the reference manual, so that you all have an idea of what to expect. So let's start off with concrete. So this is you all should have this. Let me close that. There's actually, the concrete section in the manual is really short. It used to have a lot more in it. There was stuff on doubly reinforced sections and T-beams and all of that. Not really the case. This first page goes through just some basic notation and pedigree information. You know, you've got your rebar properties, rebar diameters, rebar areas, all of your notation. You know, what is A sub S, the area of tensile reinforcement? What's beta 1? Remember, that's that factor for the depth of the stress block. You've got your stress block provisions graphically displayed here. Strain conditions. Remember, for reinforced concrete design, your resistance factor, phi. Remember, you don't just say it's 0.9, even though more often than not it is 0.9. It depends upon the strain in the steel, which if that's a little rusty, no big deal. We're going to have an example going through that type of stuff. Let's see. For beams, remember your fundamental equation for nominal moment capacity. Remember, your nominal moment is ASFYD minus A over 2. Remember, you can calculate it this way as well, but I'm lazy. I'd rather multiply less stuff than more stuff. What else? We've got shear capacity. I wouldn't expect to do a full-blown shear design. That's really not what I would worry about on the exam. If you can calculate basic shear capacity, you're probably going to be pretty good. And on columns, all we're worrying about is short columns, no buckling or anything like that. Pretty straightforward stuff. And lastly, those of you in concrete design probably remember this at the very end. That's your beam column interaction diagram. Remember, if you've got axial loads and moments, you can use this to at least arrive at a target reinforcement ratio. I'm actually not going to cover this tonight just because, in my opinion, the purpose of this session is to just get you thinking about a lot of this stuff again. I don't want to dive too far into the nitty-gritty details regarding concrete. Bless you. Now that's concrete. Steel design. How many have had steel design in here? Okay, all right. I thought it was just you two, but I just wanted to make sure I wasn't off. So for you two, here's some stuff that should be somewhat familiar. Let me get the lights adjusted. You all can actually see the TV a little easier. Okay, so you all have the steel component section as well. So the first thing that's actually in there is the beam section. So remember your plastic moment capacity and then lateral torsional buckling. You've got your definitions for your moment gradient factors, CB, as well as tabulated CB values for various cases. Remember, we talked about this near the very end. We also have the column buckling equations. So all that stuff's there, so you can calculate phi/pn per columns. You've got all the stuff for tension members. Now, one thing I should point out for you steel design folks, when you do net area, the manual lists the net area as the diameter of the hole plus the 1/16 of an inch, and then the diameter of the hole is the diameter of the bolt plus 1/16. So remember how we added an 1/8? That's how it's notated in the manual, so just so you're aware. So if you see that, you go, wait, I thought it was an 1/8. That's why. Basic shear lag factors, your U equations, block shear there at the very right. Here's just a table of some basic wide flange properties. So, based on a W24 by 68, there's the area, flange dimensions, web dimensions, moments of inertia, all that jazz. You all are aware of all of that. Remember this, that's your ZX table. Remember in design mode, remember which one do you select? Select the bold row because within that group, that's the lightest shape. Notice how there's no ASD. This is all LRFD. Remember in the manual how we picked the blue numbers, not the green numbers? Well, that's because the blue numbers corresponded to LRFD, no ASD. Lastly, beam LTB curve charts, K values for columns, single and columns and frames, your KL over R tables for critical stress, and then this is your column design chart. Remember how we went to table 4.1 to select shapes? That's what we've got here. So in steel design, you can probably expect to select beams and columns more readily than you would in concrete design. Because if you remember in concrete design, beam design is pretty iterative, and it takes a while. I wouldn't really expect a very complex problem in that world. Really more beam analysis, FEMN, stuff like that. All right. Sound good? Does anybody have just any general questions before we get started at all? Yeah, a little bit. Some of this, yeah, let me say this. Some of them yes and some of them no. Some of them really are target questions. But I would argue that's more on the steel design side than the concrete design. Concrete design, by and large, is probably a little bit more review. And I'm actually going to take much longer doing these problems than you would really need to on the exam, because a lot of this stuff on the exam is plug and chug as long as you know what you're plugging and chugging. Sound good? So utilizing the review manual handouts and everything there, we're going to go through a lot of these problems. Now, before we begin, who does not have a calculator? Good. Well, I like to see. Make sure that your calculator meets FE guidelines. You can go onto the NCES website and follow that. We pretty much use the Casio pretty religiously within our program, and it meets standards and whatnot, so you're good. All right, let's just go ahead and get into it. Okay, so we're starting off with reinforced concrete design when we've got our first problem. So we've got a beam that's 10 foot long. It's got the cross-section shown, so it's a 12-inch wide beam. Remember, D is that effective depth. It's 15 inches. We got 3 number 9 bars serving as tensile reinforcement. Now, this beam is subjected to a uniformly distributed service dead load of 5 pounds per foot. That's not a lot at all, but it's really meant to sort of get you thinking about structural analysis and being able to handle that uniformly distributed load as well as the point load that's coming. So we're going to take FC prime to be 3 KSI. We're going to take FY to be 40 KSI. And then based on this information, what is most nearly the maximum allowable live load using LRFD or using ultimate strength load combos? We've got A, B, C, and D, and so on and so forth. So everybody good? Okay. So the first step, we've got this beam. I mean, the question's asking what is most nearly the maximum allowable load. That probably means we need to determine what is the capacity of this beam. Make sense? Sound good? So we're going to go through and determine the ultimate capacity of this section, and this is really probably going to get your brain thinking about a lot of this stuff, this reinforced concrete stuff. Okay, so problem 1. Okay, so we've got our beam. What do we got going on? Okay, we've got our reinforcement. Now, our reinforcement is 3 number 9 bars. So what does that mean in terms of quantities for design? What do we know? We know the area of steel is going to be what? Y'all thinking about all this. Keep in mind, we're only using the steel or the concrete stuff for now. Page 1 of that FE reference manual, if you look at page 1 for the steel, or for the concrete, that's the steel section right there. Go to that one right there. There you go. And say it again. 3 inches. No, not 3 inches. 3 square inches. Okay? Because the area of a number 9 bar is 1 square inch. Okay? Now we've got a B dimension of 12 inches. Remember that notation? B was the width of the beam. And then the effective depth is from the top of the beam to that tensile layer of rebar, and that is a value of D equals 15 inches. Remember that? Okay. Now, let's bring back some of those assumptions, because a lot of this stuff I'm going to draw here is going to be pretty valid. Let's see if you all remember this. So let's start off by talking about the strains, okay? So let me sort of something about like that. Okay. So we're going to start off and draw the strain profile. So if you remember, the strain profile is going to look something about, I don't know, like that. Remember that? And so this strain is what? Epsilon sub s, the strain in the steel, right? Let's do some dimensions. This dimension, if you recall, anybody remember what that is? That's C. Exactly right. That, remember, from the top of the beam to the point where there's no strain, that's C. That's not the depth of the stress block. Remember, the stress block comes a little shorter than that. Okay? So if that's C, then this is D minus C. Everybody remember that? And we can use that similar triangles ratio to determine what the strain in this steel is once we get C. Now, in order to do that, we need to know what the maximum strain in the concrete is. Anybody remember what the maximum strain in the concrete is? It's a constant value. You're on to something. No. The point. Okay, I didn't do that. The lights just sort of randomly came on. What's that? Something like that. Okay. All right. The 0.85 was the width of that stress block. Remember, the maximum strain was 0.003. Y'all remember that? Remember, that's the maximum usable strain. You'll see an equation that we'll use here in a second. You go, oh, now I remember. Just bear with me. Remember, we would calculate the strain in the steel by saying 0.003 D minus C over C. Now, is that familiar? That should be familiar. And that's, we came up with that by recognizing that maximum strain was 0.003 in the concrete. Just think about it like this. 0.003 is to C as whatever this strain is to D minus C, right? And then that's how we came up with that equation. All right. Sound good? Now, that is our strain profile. Let's talk a little bit about our stress profile. All right, so here's our stress profile. So the first thing I'm going to do is I'm going to say, all right, that's the neutral axis, right? Now let's start off with the steel, okay? If you recall, the steel is a solid, just uniform tensile force right there, T, just a single force. Now remember, we right off the bat assume that the steel yields, and if you remember, ACI requires that it yields. So that is AS times Fy, right? Just the area of steel times the yield stress will tell us how much force is in the steel when it yields. Sound good? Now, for the concrete, remember, in actuality, if you recall, in actuality, the stress profile looks like this. Remember, it's nonlinear, and we would have to integrate all of that. And I don't like integrals. I like to avoid that if all possible. So I propose to you that the stress block looks something about like that. Something like that, okay? Now, how wide is that stress block? It is 0.85 FC prime. Remember that? Now, the depth of that stress block is what? Remember, that's A, right? It's not C, it's A, right? Is that bringing it back? No, it's been a while since some of you all have done this, right? But this should be somewhat familiar. So far, so good? Okay, all right. Now, let's go through our stress profile and let's see what all do we know and what all do we not know. Okay, here's our stress profile. We know Fy, right? For this beam, what is Fy? 40 KSI, not 4, but you're right, you're exactly right. So we know Fy is 40 KSI. We know FC prime, right? The compressive strength in the concrete, and that is, what's that? No, it's not 30, it'd be 3 KSI, because we got to divide by 1,000, 3 KSI. If we could craft up some 30 KSI concrete, I'd be a millionaire. Actually, no, there is ultra high performance concrete that can get in the 20s, so but that's another topic for another day. All right, now, pop quiz. If FC prime is 3 KSI, what is beta 1? It's right there. Probably want to look on the left in the notation section. 0.85, there we go. Remember, beta 1 is 0.85 anywhere below 4 KSI, okay? Why is that important? Because if you remember, A, that depth of that stress block is equal to beta 1 times C. Remember that? So this depth of this stress block right there is beta 1 times C. Once we get A, that beta 1 will help us out later when we need to determine strains. All right, so far so good? Now, we've got this compressive force inside the beam. That's the stress in the concrete. We've got this tensile force inside the beam. That's the force in the steel. I propose to you that if we don't want this beam running away from us, that C has to equal T. In other words, the force in compression has to equal the force in tension. All right? Now, the force in tension is, here, let's set an equals here. The force in tension is AS Fy. Make sense? What is the force in compression? Somebody tell me, how would we calculate the force in compression? Think stress times area. Okay, all right, there you go. All right, you're exactly right. So 0.85 FC prime times the area that it's acting over on the beam, which is A deep and B wide. Does that make sense? Everybody good? Okay, so what don't we know? We know the area of the steel. We know Fy. We know well, obviously we know 0.85. We know FC prime. We know B. We do not know A. We do not know the depth of that stress block. So A is AS Fy divided by 0.85 FC prime B. And now we can plug and chug. So on the bottom, we've got 0.85. We've got FC prime, which is 3 KSI. We've got B, which is, what, 12 inches? All right. And on the top, we've got, let's see, 3 square inches. And we've got Fy, which is 40 KSI. All right. So plug and chug, what do we get? Making y'all do a little bit of work this evening. Just don't crack under the pressure. Thank you very much. I work hard at this. What's this? 3.92. So I propose that that stress block must attain a depth of 3.92 inches such that the force in compression equals the force in tension. Now, that helps us out with the forces. Okay, let's talk about moments. Now, how do you, in general, calculate a moment? It is a force acting at a given distance, right? Make sense? So, which force do I use? Do I use the force in compression or the force in tension? Well, it really doesn't matter because they equal one another, right? Now, because I'm lazy, if I have to calculate the force in compression, I have to multiply 4 things together. The force in tension, I'll have to multiply 2 things together. So I'm just going to use the tensile force. So my force is going to be ASFY. Now my moment arm. Well, my moment arm is going to be the distance between these 2 forces. So this compressive force is really going to be, collapsed, centralized right there. Make sense? If you have a uniformly distributed load, you can collapse that into a single point load in the middle, right? So my question to you is, how far is it from here to here, right? What is that moment arm between those two forces to generate that force couple? Well,
from the steel to the very top is D, right? And from the top to that compressive force is not A, it's half of A, right? So my moment arm is D minus A over 2. So I propose that the moment capacity, if this moment arm is D minus A over 2, I propose then that to calculate the moment capacity, Mn, it is a force acting about a given distance. So if you want a behavioral explanation, this part is the force, and this part is the distance. So now we can plug and chug. So AS, that is 3 square inches. FY, that is what? 40 KSI. And then D is, what's D? 15 inches minus A, which we just calculated, 3.92 over 2. And what does that give us? Say it again. 1565 what? There we go, inch kips. Because of our units, we're inputting KSI and then inches. Now, if I say, okay, I don't like inch kips, I want to convert that into foot kips, what do I do? Divide by 12. So divide that by 12, what do you get? 130.4 foot kips. So far, so good? Now, that is a nominal moment capacity. Remember, when we're doing ultimate strength design, or LRFD, we must adjust that moment capacity by a resistance factor to obtain a moment capacity we can use for design. Sound good? So, in order to do that, we need to determine what phi is. Okay, so we need to determine phi. So we'll say phi. Now, phi in steel design, you just look it up. In reinforced concrete design, when we're talking about beams and bending, phi is a little more intricate because it's a function of the strain. Okay, so let's start off with that. All right, we've got an A of 3.92 inches. And remind me, what was beta 1? What's that? 0.85. So if A is beta 1 C, how do we calculate C? A over beta 1. So 3.92 inches over 0.85 gives us what? So far, so good? Now that I've got C, I can say, all right, let's calculate the strain in the steel. And remember that it's 0.003 D minus C over C. So that is 0.003. And then D was what, 15 inches? Minus 4.61 over 4.61. What does that get, yield? No pun intended. That was a good one. I'm sorry, that was a good one. .0067. Now, remind me, what does that mean? Phi doesn't equal 9, it equals 0.9, okay? And the reason why is because that strain in the steel, so since the strain in the steel is greater than that magic number of 0.005, that means that phi is 0.9. And remember, you can kind of think of phi as your safety factor. We're taking that capacity that we're calculating, the nominal capacity, you can think of that nominal capacity as what would happen if we went down to the lab, put this beam under an actuator and loaded it till it broke. We say, all right, instead of using 130.4 for the purposes of design, I can't really use that. I got to reduce that a little bit. And I'm going to reduce it to 90%, 0.9. So therefore, phi mn is 0.9 times 130.4 foot kips. Phi mn is what? .36 foot kips. All right. Now I want to just sort of take a step right here, take a step back. How are we doing so far? So far, so good. Any questions? Anything not remembering? You tell me. Everybody good? Okay. Now, let's go back to the problem definition, okay? What is the problem asking for? It's asking for the maximum what? A maximum allowable live load. Okay, so let's sort of see if we can remember what's going on there. Okay, so I'm going to strike a line. All right. Back to our fundamental basics of design. Phi mn has to be greater than or equal to mu. Remember that? In other words, that the resistance, how much the beam can support, must be greater than or equal to the loads that we're subjecting to it. Now, we don't just put loads on the beam directly when we're utilizing LRFD. We factor those loads. We adjust them by appropriate factors. So since we're dealing with dead and live, phi mn must be greater than or equal to what? 1.2 m dead plus 1.6 m live. Remember that? 1.2 times the dead plus 1.6 times the live. Now, one particular point I'll make about this problem, what dead load must all beams be able to withstand? Their own self-weight, okay? Now, in order to determine the self-weight of this beam, theoretically, we would need the beam's width and the beam's height. Do we have the beam's height? No, we don't. We only have its depth. Now, we can make a guess and say its real height's about, what, 18 inches, because it's usually 3 more than the depth. But I'm actually just going to conservatively neglect it. When you look at the numbers you'll see here in a little bit, it probably wouldn't matter anyways. But you can make a guess if you need to. For the purposes of this, we're just going to neglect it. All right, so we need to determine the maximum allowable live load. Keep in mind, this whole time we're talking about a problem that looks like this. We've got, here's our beam. We've got a, uniformly distributed dead load on there. Some dead load, and what is it, 5 pounds per foot, right? It's 5 pounds per foot, isn't it? It was really minor. The whole point was just to go into the structural analysis. The 5 pounds per foot really wasn't supposed to influence anything significantly. And what we're trying to find is, what is that? That PL at midspan. All right, so let's do a little bit of things here on the side. Let's do a couple things here on the side. All right, we know that the distributed load is 5 pounds per foot, or 0.005 kips per foot. Now, how long is the beam? 10 feet. So if this is the case, how would I calculate that maximum dead load moment at midspan? I'm actually going to ask you, Mr. Schaffer. Well, if you remember at our last session, we said it was WL squared divided by something. Wasn't 4. 8. There we go. WL squared over 8. And if you're unsure, there are formulas in the manual. Now, they're in the mechanics of material section within the manual, but they're there. But does everybody remember that formula, WL squared over 8? That's the maximum moment formula for a beam subjected to a uniformly distributed load. All right. So what do we have? We have 0.005 kips per foot times 10 feet squared over 8. And yet this is going to be a very negligible moment. It was just trying to get you all into the groove of things, making you think about all this. What do we got? All right, 0.063 foot kips, right? Now, just curious, does anybody remember what the moment formula is for a point load at midspan? Does everybody remember that? What's the maximum moment? In other words, it's, if we wanted to compute that, actually, let me do this over here. Well, hold on. Let me give myself a little room. 0.063 foot kips. Now, for that uniformly distributed load, maximum moment is WL squared over 8. If you've got a point load at midspan, does anybody remember what the maximum moment formula is? It's okay if you don't remember it. It's okay. It's no big deal. Well, watch this. Let's see if you all remember this. Okay. Let's say, do a little bit of basic structural analysis here. Let's say I have a single point load at midspan. Okay. What are the reactions going to be? P over 2, right? That's P over 2. And that's P over 2, right? And this dimension here, that's L over 2. That's L over 2, right? So if I say, all right, and I want to draw the shear diagram, what's the shear diagram look like? I go up P over 2, right? No change. Go down P, so that puts me at negative P over 2. No change. Brings me back up, right? So this is P over 2. This is minus P over 2, right? And then to obtain the moment diagram, we integrate the shear diagram or calculate the area under the curve. So what is this area right here? What? There we go, PL over 4 and minus PL over 4 here. And what's our moment diagram going to look like? Well, this is a constant shear diagram, constant shear, constant slope. So up to PL over 4, down, back to 0, right? Everybody remember that? So I propose that whatever moment value, whatever moment value we solve for the live load, we're going to calculate the actual component or the moment due to that point load as PL over 4. And I'm doing P sub L because it's a live concentrated force. Everybody remember that? Any questions? Okay, so I want to go back to this, to that inequality. All right, what do I know? Well, I know phi mn, and I now know the m sub d. I know the dead load moment. So could I solve for the live load moment? Okay, so how would we do that? We'd say, all right, phi mn, what is that? Minus 1.2 md over 1.6, that has to be greater than or equal to PL, right? Fair point? Or ML, not. I'm getting ahead of myself. So far, so good? So if I flip that around, I can say, all right, ML must be less than or equal to what? Well, what's phi mn? Well, we're gonna do that here in a second, but I just want to do my plug and chug one at a time. What is phi mn? It's like what, 117.36 foot kips minus 1.2 times m sub d, which was a really small number. You could almost neglect it. And then 1.6 is constant value. So m sub L must be less than or equal to what? .3 foot kips. All right. Now that's saying our moment must be less than or equal to 73.3 foot kips. The moment is PL over 4 must be less than or equal to 73.3 foot kips. So I propose then that PL, the actual load, must be less than or equal to 4 over L times that 73.3. And what was L? 10 feet? What was 10 feet? So that's 4 over 10. So what's 4/10 of that? .3 kips. So what this is saying is that in order to meet strength requirements, that live load must be less than or equal to 29.3 kips. So if I go back to the example and I say, all right, here's the example. What is most nearly the maximum allowable live load using LRFD? It's B. Not really. But that, like I said, that's a fairly involved problem. That's a fairly involved problem. You know, maybe a more realistic problem might be just what's the capacity. You know what I mean? I'm not saying that, I don't want to stand up here and say always is and nevers. I mean, is there the potential that you get asked something this convoluted? Yeah, but personally I believe this is upper echelon. This is about as conceivably bad as it gets. And I sat here and explained the whole thing. You know what I mean? It took me a lot longer because I'm going through and explaining it. So, how fast could I have done it if I didn't explain it? I have an unfair advantage because I do this all day, every day. So I could probably do it pretty quickly. But I do this all day, every day. You know. Now ask me about an open channel flow problem, and it might be a little different. So it might take me a little longer on that. So the next problem goes quicker, I promise. All right. Next problem's a lot quicker. Actually, I think the next two problems are a lot quicker. All right. This one was designed to be a little long. If you got through this one, you will definitely get through the next two. Any questions? Oh. Keep in mind, I am doing hard problems for a reason. I want you to get the simple stuff. That's the whole point. All right. Any questions? All right. Let's look at example 2 then. So for example 2, for the singly reinforced concrete beam shown below, what is most nearly the ultimate shear strength, VVN? Okay. Now we've got a width of 18 inches, right? We've got an effective depth of 33 inches. Now, remember, when we're looking at shear capacity, we're more interested in our stirrups, right? Those hoops that go around the reinforcement. So I've got number 3 stirrups, and they're spaced at 12 inches, okay? Now, I want to determine what is most nearly the ultimate shear capacity, and there we go. Keep in mind, sometimes you are provided some superfluous information on these problems. In other words, there's some information you've been provided that you don't need, okay? And we'll see that as we go. Now, let's go into your handout, your reinforced concrete section from the code, and tell me, how do we compute the shear capacity? Okay, so obviously we're going to calculate phi VN. So let's start off with this. What is phi for shear? Phi for bending was a little more complicated. What is phi for shear? Now that was for columns, remember? But you're on the right track. Let's say it again. 0.75. Now, if you're unsure, look at page 1. Right here on the bottom. See it? Phi for shear and torsion, 0.75. And there you go. What's that? That's the whole point, is so that you understand this. Okay? Now, if you remember, for shear, we really treat it like an equilibrium. You know, you have, it's looking like sum of forces in the y direction. We have a shear contribution from the concrete and a shear contribution from the shear. How do we calculate the shear contribution from the concrete, the V sub C? 2BWD square root of FC prime. Everybody remember that? 2BWD square root of FC prime. Does everybody see that? Second page, about right in the middle. And it literally says beams shear. And there it is. Okay? So how do we calculate V sub S? AV Fy d over S. Remember that? Remember, it's that d over S is sort of the amount of stirrups per beam depth. We're trying to figure out how many stirrups cross a beam depth, because that's how we assume the beam's going to crack that 45 degrees. All right. Everybody. Oh, what's a stirrup? I'm talking about, no, that's fine. You haven't had the class. I'm talking about these hoops. These hoops. All right. That's a stirrup. Okay. So now you're going to test my three-dimensional artistic abilities here, so I'm going to do my best. So if you've got a beam and it goes like this, right? Okay, so we'll say that here's the supports, something like that, right? Okay, you're going to have, you know, some bars go like this. That's the tensile reinforcement. But to tie all that together, and to provide shear reinforcement, you're going to have, you know, some hoop steel here, and, you know, some stirrups like that. Those are stirrups, okay? You'll find when you do shear design that if you have, let's say, a simply supported beam, you put more stirrups towards the supports than you do the middle of the beam. And why is that? There's more shear towards the supports than there is toward the middle of the beam. Make sense? Good? All right. What's that? They're called stirrups. What? I've heard hangers too. I've heard that too. All right. Everybody good? I tested my three-dimensional artistic abilities. All right. Okay. Problem 2. Okay. So we handle this one step at a time. We start off with the shear contribution due to the concrete and the shear contribution due to the steel. So let's start off with V sub C. Okay? Now, V sub C we calculate as 2 BWD square root of FC prime. This is going to test y'all's memory banks a little bit. Okay, so let's start off with this. 2 times, what is BW? Remember, BW is just the width of the web. When you're dealing with a rectangular beam, it's just the width of the beam. So how wide is this beam? 18 inches. All right. D, what is D? 33 inches. All right. What is FC prime? Say that again. Exactly right. Remember, when you do a square root of FC prime, you put in PSI, you get out PSI. Remember, that's that empirical relationship. Do not do a square root of 4. You will get the wrong answer. Hopefully. I said that about 946 times last semester. So, all right. So, what do we get? $75.4 what? Did you already divide by 1,000? You don't. So if you actually do the math, you get like 70. Let's carry it out. Let's carry it out.
Yes, 75,135.7
Pounds. So that's 75.14 kips. Right? I got everything written down right. Okay. All right. Okay. Now that's V sub C. Okay. How do we calculate V sub S? V sub S is AV FYT D over S. Right? Now, a couple things. Let's start off with AV. Okay? AV is the area of the steel resisting shear. Okay? So what type of bars are we using for the stirrups? Number 3s. What is the area of a number 3 bar? No, you're talking about the diameter, and it'd be 3 over 8. 0.11. Okay, so the area of a number 3 bar is 0.11 square inches. So what's our area in shear? It's twice that, remember? Because, remember, here's your beam, right? Let me go down here. So here's your beam. You know, here's the support it's sitting on. Here's the reinforcement steel. And here's all our stirrups, right? And remember, we assume that that beam cracks something about like that, right? Okay, so if I look, how many bars is that crack going to cut through? Right? Because keep in mind, you know, 3-dimensionally, the beam looks like this, right? And the stirrups are kind of, what, they're going like that in 3D? So that crack, if I cut right through that beam, it's cutting through 2 bars, right? Make sense? So the area in shear is 2 times 0.11 square inches. Y'all remember that? Remember, if you've got a U-shaped stirrup, you multiply that by 2. Now, what's FYT? That's the yield strength of the tensile yield strength of that reinforcement. 60 KSI. Okay. What is D? 33 inches divided by S. What is the stirrup spacing? 12 inches. And what do we get? Well, we're going to get kips here. Whenever you see a square root of FC prime, it represents an empirical relationship. And let me take a step back. An empirical relationship is one where the mechanics are so damn complicated that what we end up doing is we say, okay, let's build a bunch of reinforced concrete beams. Let's go down to the lab and break them, because any day with controlled demolition is a good day, and let's record the data. And when we get that data, let's see if we can map a simple equation to that data. And what you find in concrete design is that the square root of FC prime matches things quite well in a lot of cases. But because of units, when you put in PSI, you get out PSI. It's just, it's a little wonky, but it's something you gotta just pay attention to. All right. Okay. What? I've used wonky for a while.
You're just trying to be like Dr. Ford. I swear. He's like,
Maybe it's the other way around. You ever think about that? Oh, I see how it is. All right, what do we get for this? 36.3 kips. So I propose that Vn is Vc plus Vs, which is what? Is that our answer? So phi Vn is 0.75, which is what? Not too bad, right? This is a whole lot more basic, right? Feeling a little better about a problem like this? Now, keep in mind, okay? Keep in mind, all right, if you don't remember some of this stuff, like you go into this shear equation, you go, what the heck does S stand for, okay? Go back to your handout, okay? Remember, this is where we found that equation, right? V sub c, 2bwd squared of fc prime, v sub s, so on and so forth. If you don't remember what S is, look at the front page right here. What is it? It's a big notation list. Read S. Spacing of shear ties measured along longitudinal axis of member. Right there. Even tells you what units to use. So, sound good? Yes, sir.
so I was thinking about that. I just looked at this equation and I was like, well, what the hell does that mean? And I was looking around here and I was like, well, we're in, I don't know, maybe a couple minutes of test, but I've not failed the test.
Okay. That's a good question. That's a good point to make, that you know, maybe you don't know what some of these equations represent. Two things. One, if you've never had reinforced concrete design and you're in here and I'm just throwing out V sub C's and 0.003 D minus C over C, it might seem like second nature to some of them because they've been through 15 weeks of reinforced concrete. You haven't. One thing to keep in mind, we're only talking, though, about 3 or 4 questions on the test. We're not talking about the entire test. I mean, keep in mind, the largest section on the test is math, you know, and everybody in here knows that, you know, and then you've got prob and statics and all that. A very significant chunk of the test will be stuff that you do know. I mean, everybody's going to find that one question like, I never took hydrology, you know, and it's okay, you know, so just do your best, you know. The thing about the FE, you're not asked very significantly difficult problems. You're just asked a lot of them, okay?
When did you take the FE?
When did I? I took the FE in 2008, in October of 2008. All right.
Do you have your PE yet?
I'm taking that next year. So that's next year. So I know it was in 2008 because that was the year before I graduated, and I know it was in October because they only offered the FE twice a year then, April and October, and I took it in the winter. It was cold, so yeah. What's that? Well, when I took it was 8 hours. Yours is only 6 hours, so. More time equals more problems. What's this?
He's like 16 hours.
That's the SE. And I've thought about taking that. I just don't know if I have the, what's that?
How many professional structural engineers do you have?
Well, if they're in California or Illinois or any state where seismic is a big issue,
They have to have it.
yeah. The SC is primarily geared towards the difference between having a PE in structural engineering and an SC. It's really geared towards a lot of seismic stuff. So the way the test is split up, you have buildings, gravity, buildings, lateral. Bridges, gravity, bridges, lateral. And the lateral stuff is all wind and seismic. So yeah, I just don't know if I have the patience for 16 hours.
If you stay with the mini, you don't need it.
No, I don't have to worry about it. But I just want the damn letters after my name. It's not like I'm going to use it. So
Make a stamp. Or a stamp on the mail.
yeah, that's what I'm going to do. I certify this Christmas card. Okay. I approve this message of Merry Christmas. Okay. All right. Another simple one in reinforced concrete design, and this one is really simple. Okay, for the short columns shown below, we've got an SC prime of 4,000 psi, Fy of 60,000 psi. What is most nearly the ultimate axial strength VPN? Tie reinforcements are utilized. Remember, in reinforced concrete design, there were different factors with tied columns versus spirally reinforced columns. You all remember that? But if you look in your reference manual, go to the section that has columns. There's only 3 pages, so you can find it pretty easily. Look at right here on the right on the second page. It says short columns. I see equations for tied columns. What about spiral columns? Are they there? No. So there you go. So you're not going to get those. So pretty straightforward. So the column is 16 inches by 16 inches. So you know what? I'm not even going to pull the board up. All right. What's the gross area of this column? It's 16 by 16, which is 256 square inches. What's the area of the steel reinforcement? Those are 8 number 9 bars. So nope. 8 square inches. All right. We have an FC prime of 4 KSI, Fy of 60 KSI. So I propose that VPN is 0.8 phi times 0.85 FC prime AG minus AST plus AST times Fy. So that is 0.8 times what's phi? No, phi. No, that's fine. FC prime. There we go, 4 KSI. So basically what we're saying is it's the ultimate capacity of the concrete, which there's not 256 square inches of concrete there. There's 256 minus the steel, right? So that's why we're doing AG minus AST. So 256 minus 8, that's what, 248? Plus 60 KSI times 8 square inches. What's that? What's that? That's a lot of numbers. One thing you'll find is that I think in a few weeks I do my math session. And my math session, it's a lot of quick problems. It's not these super massive long problems. It's a lot of short problems. So. That one's not so bad, is it? What's that? These last 2 are manageable. In all honesty, those last 2 are very expectable problems on the FE. Okay. Before I move on. This is it for reinforced concrete design. This is all I'm covering. Any questions? All right. So steel design. Yes, sir.
Any like example, maybe like conceptual questions that they might?
There are some, but I don't want to get too far into it. Here's one I can think of, and I don't have a multiple choice one in my head, but here's one that I can think of off the top of my head. What does epoxy coating rebar do to the development length? It makes it longer. Now, if you've had reinforced concrete design, was that a simple one? A lot of this is, when I say, oh, if you've had reinforced concrete design, it's a piece of cake. A lot of those types of conceptual questions are going to be the case if you've had any of these classes. Now, let me give you the background on that question so that you all understand where that's coming from. So, development length is how far you need to encase a piece of rebar into concrete in order to develop its full capacity. In other words, if I got a big thing of rebar and I've got this mass of concrete and I only encase it about 1/8 of an inch in, I'm probably strong enough that I can yank it out, okay? But if I encase it 12 feet into this massive concrete, I'm not ripping that thing out. But there's a certain magic length where it doesn't matter if it's 10 feet in or if it's 110 feet in, you're still just going to fail the rebar before you fail the concrete, and that's going to be it. We call that the development length. When you coat rebar in epoxy, you make it slicker. So if you epoxy coat rebar, you require a longer development length. Does that make sense? Okay, that's the background. And those are the types of questions that are going to be the case. Like here's I know we're getting way off topic, but here's a fluids question. If you have a pipe from one end to the other and the area increases, what does that do to the velocity? Decreases. There you go. In all seriousness, that is a type of conceptual question you could get. I'm sure there are probably more refined ones, like what does a Reynolds number of 50 mean? That's laminar. I remember that. It's like you have to be like 50,000 or something, then it, yeah. So stuff like that. Those are the types of conceptual questions you could get, stuff like that. That make you feel better or worse? Okay. All right. Whoa. We're going to have to erase all that. Does everybody have everything up here? Okay. Now, I have a feeling that for the rest of this, it's going to be sit back and enjoy the show, right? For most of you. So I'll do my best to try and expedite this, but I also want to make sure this is an adequate review for the folks that are in here. So what we're going to do for the steel portion, at least for example 4 and 5, is it's going to be a lot of design. Okay, so our first design problem is a column design problem. Now, regardless of if you've had steel design, you have had mechanics of deformable bodies. And in that class, you learned that things in compression like to experience this particular type of phenomenon known as buckling. Things in compression like to buckle. Okay, and the capacity of a column is a function of its length as well as its effective length factor. You know, a pin-to-pin column has a different buckling capacity than a fixed column. You all remember that from mechanics of deformable bodies? Okay. All right. So that K value that you see in that equation, or in that example, Kx equals Ky equals 1, that's representing a pin-pin column. That makes this pretty easy. So let's just go through this, and I'll try and keep this pretty straightforward. So from the choices below, what is the lightest wide flange shape? 50 KSI steel. Any design problem on the FB is going to be 50 KSI. What is the lightest shape that's available that can resist a service dead load of 125 kips and a service live load of 200 kips using LRFD? So first off, if you don't even know anything about steel design, Dead load and live load, what do we need to do? There we go. 1.2 dead plus 1.6 live. There you go. Catching on. All right. So what is 1.2 times the dead plus 1.6 times the live? You tell me. And I might actually just use this board in case this marker decides to transfer to the PDF. So just so I have it for my benefit. The folks on, if anybody's watching the video, they'll be able to write this down anyway. So. 470, you said? Okay, 470, and I'm going to write that here. So my design load is 470 kips, okay? Now, when you're dealing with columns, you have the length, but you have the effective length. Now, when you're dealing with a column, if I have, here's a column and it's loading like this, assuming it's doubly symmetric, it can either buckle out this way or it can buckle this way. Make sense? Either going like that or like this. And one of the ways that we can determine that is looking at its slenderness. It's KL over R. But since we have a column that has the same K values in both directions and the same L values in both directions, I propose to you that the y-axis is going to govern, and we're going to see that here in a second. So let's calculate KY, LY. So that's going to be what? 1 times 15, 15 feet. So far so good? Okay. And we're going to choose the lightest column that can resist these loads. Everybody good? All right. Now I want to go to the steel manual real quick. Oh, okay, it didn't transfer over, so that's good. Okay. So now I'm in the other handout. So you can take that reinforced concrete handout and sort of put it up. Well, I don't know about all that, but put it off to the side. Okay. So I'm in the steel handout. Now the first main chunk here is on beams. I'm going to go past that and get into here. Okay. Now I just want to look at this table real quick. Okay. So this is a table that is listing section properties for various wide flange shapes. So for instance, a W21 by 50. Let's see if you steel folks remember. The 21, what does the 21 mean? Yeah, the depth. It's about how deep it is. Like you can see it's 20.8. Its nominal depth is 21. What does the 50 mean? Pounds per feet, how heavy it is. Okay, so if I cut through this W21 by 50 with a samurai sword or a lightsaber, depending on whether or not I'm a sci-fi fan, I'm going to see that eye shape having an area of 14.7 square inches. The web thickness is going to be 0.38. The flange thickness is going to be 0.535, etc. Everybody getting this? So the flanges, just so we're all clear, are the two flat parts, the web, the part in the middle. Everybody good? Okay. Now, what I want to look at are the moments of inertia. So look here on the x-axis. I've got what? 984, y-axis 24.9. You'll find when you take steel design, I don't really talk about the x-axis and the y-axis. I talk about the strong axis and the weak axis. And in general, for shapes, the weak direction is the y-axis. That's why when you have beams, you orient them so the flanges are like this. You don't take a beam and orient it like this, okay? Because it's really flimsy this way. Make sense? Now, because we have the same length and same bracing length in both directions, the L in both directions, and we have the same K, automatically all I need to do is look at the weak axis. Now, we're in column design, so I'm going to show you how this is going to work. We'll scroll past this, scroll past all this, and I'm actually going to be on this very last table, on the very last page. So it should look something about like this. Okay. Everybody here? Okay. So if you look here on the very, very left, it says KL or the effective length with respect to the least radius of gyration RY. This entire table is built based on the weak axis capacity. When you take steel design, you learn how to check this for the strong axis capacity. But if not, if you know the weak axis governs, then this is pretty basic. What is KL for this column? 15 feet. Okay, all right. So that means I'm looking at this row. Everybody see that? That row with KL is 15. I'm looking at that row. Okay? I'm going to scroll up a little bit. All right. So let me circle that. This is the row I'm looking at. Okay. Now what you're seeing on these columns are the given shapes. So for instance, let me look at this first column. This first column here is a W14 by 74. Everybody see that? Now I propose that if you have a column that's a W14 by 74 and it's 15 feet long, assuming the weak axis governs, its capacity is 667 kips. Does everybody see that? Okay. All right. W14 by 68, 608. Everybody good? Now, what are the four columns in our choices, the A, B, C, and D? What are the four columns? W12s, okay? Specifically, it's the W12 by 50. It's those, right? Okay. Now, right off the bat, what's our factored load? 476, or 470, right? Can we use a W12 by 40? No, it's too weak. What about a W12 by 45? What about a W12 by 50? What's the answer? A. Simple, right? Not too bad, right? What I'm trying to do with the steel portion of the review is I'm trying to highlight key points that if you haven't had steel design, this is some stuff that you should be able to do. I'm not saying that you're going to be able to do everything, but these are some pretty basic problems. And my folks that have had steel design, this is pretty basic, right? This isn't bad, all right? Any questions? Okay, all right. Everybody good? All right. Okay. Okay, let's look at example 5, okay? A W24 by 55 is to be used as a simply supported beam, a span length of 12 feet to support a uniformly distributed load. Okay, taking CB to be 1, what is most nearly the flexural capacity if only the ends of the beam are laterally supported? So if you've had steel design, this might actually be a little bit confusing because if you have a uniformly distributed load and only the ends are supported, you should be able to compute CB. But I've kept CB to be 1 to make this simple. For those of you that haven't had steel design, let me explain what's going on here. Okay? So in the world of steel design, when we do beams, we actually do beams at the very end of the class because beams, like columns, present a stability issue. Columns, as we just realized, are elements that like to buckle. Well, beams like to buckle too. You have a portion of the beam that's in compression. It wants to buckle. A portion of the beam in tension does not. There's an internal conflict going on within the beam, and the beam ultimately sort of kicks out and twists. And it experiences a phenomenon known as lateral torsional buckling. Have you ever heard that term before if you haven't had steel? Okay. All right. So that's a very familiar failure mode for a steel beam. Okay. Now, when we make our derivation, when we go through and do all the differential equations and derive all the stuff, one of the things that we do in our derivation to make it possible and make it simple is we say the moment is a constant. So we sort of, you can imagine if you've got a big equation, you got a constant, you can factor it out. That's technically not correct. I mean, look at a moment diagram. The moments go all over the place. Moments aren't constant. This term CB is trying to incorporate the changes that you get in the capacity when the moment varies. The simplest case and the worst case scenario is a case where CB equals 1. So the fact that they gave you a CB value would be very straightforward. Now, let's say they did not give you a CB value. I want you to go to the steel design page, go to the very first page. Okay? Over here on the right is a table, values of CB for simply supported beams. Everybody see that? Okay, so looks something about like this. Okay? Now, we're dealing with a beam that has a uniformly distributed load. Okay? So we're obviously dealing with this case here at the bottom. Okay? Now, when we're dealing with beams, one of the big things we need to worry about is its unbraced length. How far apart are the braces? And by braces, they could be cross frames, other beams framing into it. I mean, think you've got a bunch of beams and you got a big girder with beams framing into it. You'll see what I mean? So you've got beams, girders framing into it, cross frames, and what have you. One of the big things we're worried about is its unbraced length. So if you look here for this distributed load, look at the differences in these values. It's all a function of where the braces are. So like this second one is if you have a brace at each end and then a brace at midpoint. This one down here, if you have a brace here, 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 and here. Everybody kind of see what's going on? And within these different given elements, we have different CB values. Now what we're dealing with is this one up top where all we have are braces at the end. See these little X's right there? That's if you had a brace framing into it. Okay, bless you. All right, and for that case, CB is 1.14. Okay, now we're using a CB of 1, but that's neither here nor there. Any questions? Okay, now our unbraced length is a term that we call LB. Okay, now for this beam, since it's unbraced throughout its span, I propose to you that LB equals the length. And how long is this beam? 12 feet. So we're on problem 5 because I skipped a lot of this here. Problem 5. So for this beam, LB is 12 feet. Okay? CB is 1. So far, so good. Now, what was the shape? What did the shape look like? What was it? It was a W 24 by 55. Okay. All right. Now, I know I'm hopping back and forth on the screen here a little bit, but I want you all to sort of somewhat follow along with me on the tables here. So I'm on this steel design handout. I'm going to go past this a little bit. I want to go to this table right here. This is one of the most fundamental references that you use in beam design. It's called, I tend to call it the ZX tables. It's a very common term. ZX is what's called the plastic section modulus. You all who've had mechanics of deformable bodies have heard of a moment of inertia, and you've heard of a section modulus. A plastic section modulus, to give you kind of an idea, you calculate the elastic section modulus based on where the centroid is. You calculate plastic section modulus based on where C equals T. You all have done that before in concrete design, so it's very similar. Okay? Now, in this table, there are a lot of terms that are very important to us. So we're dealing with a 24 by 55. Okay? So what's going on here? So it's a W24 by 55, right? Okay. So W24 by 55, that's the beam on the very, very top. ZX is what, 134 cubic inches? We can write that down, although ultimately we won't need it. I'm going to use the board right here, but I'll copy this down here in a second. So let's write down some other values. Let's see. I've got phi MP, which, if you haven't had steel, that is the absolute maximum capacity of a beam. A beam cannot exceed MP, and that is 503 foot kips. I've got phi MR of 299, which that's kind of like the yield moment. It's a reduced yield moment, hence the phi MR. We reduce that because of the presence of internal stresses inside the section. Okay. We have phi BF, which that stands for beam factor, and I'll explain what that means when we look at a graph here in a second. And that is 22.2 kips. We have LP and LR, which are also functions related to its capacity. I don't want to get too heavy into that if you haven't had steel design. If you have, this should all be old hat, right? You all remember LP and LR are your LTB anchor points on your capacity plot. So that's 4.73 feet and 13.9 feet. Now, even if you haven't had steel design, what's this column here on the very, very right? What's that? On the very right. That's the shear capacity. You know, it's just, so for the design capacity of a W24 by 55 is 251 kips. All right. Sound good? Okay. All right. So I've got all that written down just for my reference. I want to go back to the. Well, actually, let me scroll up one more. All right. See right here. Okay. So we're looking at beam capacity. Now this is an expression to compute beam capacity. It's all right here. When you have a beam, just like a column, the longer it gets, the weaker it gets. I mean, if you have a really, really long column, it's going to be pretty easy to buckle it. If that column's really short, not so much, right? Well, just like a beam, the longer it gets, the weaker it is, specifically its unbraced length. Now, if your unbraced length is between these two limiting lengths, LP and LR, this is your capacity. What is the unbraced length for this beam? It's what? 12 feet? Okay. So we're in this range right here. Sound good? We're in this range. All right. Now, let me see something real quick. Okay. All right. Everybody see this? Okay. So ultimately, this is the equation that we need to use to compute the capacity of a beam. Now, I want to explain a couple things. The reason for this less than or equal at the very, very end is because of this CB. CB amplifies your moment capacity based on how the moments are, but you can't go above MP. So you can calculate this hullabaloo, but if it's bigger than MP, that's your capacity. That's not going to happen for us because we have a CB value of 1. Everybody good? All right. That's point 1. Point 2, if you notice, see how I've got this 0.7 FY SX? Everybody see that? And then I've got this LB minus LP over LR minus LP. I'll tell you what, I think we're just going to compute this directly. So the only other thing we're going to need for this section is SX. That's the only thing we're going to need. So let's go find SX. So I'm going to go into this section right here. And what is SX for a W24 by 55? What is that? W24 by 55, section modulus was at 114? Everybody see that? Everybody see that? Okay. All right. I mean, there are some shortcuts that I could show you all. I don't want to get too deep into it because I don't want to lose you in the world of steel design if you haven't had the course. So I'm going to show you a sort of roundabout way to compute some of this. So I propose your capacity expression, Mn, is going to equal the following. It's going to be CB, which is 1, times the following. MP minus, what do we have? MP minus 0.7 Fy Sx, and then LB minus LP over LR minus LP. Okay. And I'm going to do my best to try and not lose you on some of the math. Okay. Everybody good? Okay. All right. First off, CB is 1, right? So that can just go away because 1 times anything is itself. Everybody good? That's point 1. Point 2, would you then agree with me that phi mn would be phi mp minus phi mp minus phi 0.7 Fy Sx LB minus LP over LR minus LP. Would you agree with that? Everybody with me? Okay. Could I rewrite this by saying phi MP minus doing this? Would you agree with that? Everybody okay with that? I propose to you that this big fraction that you see right here, I propose to you that that is your beam factor. What's that? It is, I promise. If you take steel design, we'll learn all about it. What's that? How so? You don't just want to learn steel design? There's other things that you can take, right? No. No. Where? Oh, this is L where? Right here? Okay, this is LB. Okay. So the reason why I've formatted it in this fashion is because we already know all of this. The phi MP, that's this. That's the 503. Minus phi BF is the beam factor, and that is 22.2 kips times LB for this beam is 12 feet minus LP is 4.73. And this is literally all the math we have to do for this example. What does that come out to be? So what's the answer? 344 or, well, I'm getting A, B, C, D is what I'm getting at. B. Okay. Now, if that seemed like utter magic, let me sort of explain what was going on. Okay. Looked at what chart? Yeah. There's actually even a shorter version if you've got a good eye for it. See, let me sort of explain what's going on. Yeah, you know it's going to be somewhere in between there. You're exactly right. And it's linear. Okay? And let me explain why. Okay? Do you remember? All right. As I said earlier, if you've got a flexural element, a beam, the longer it gets, the weaker it gets. Okay. The longer it gets, the weaker it gets. If you, for a given beam, if you plot what that looks like, it looks something like this. Okay. So here's the moment capacity. Here's the unbraced length. So the longer the unbraced length gets, this is what's going on. All right? And for a beam, we define 3 regions. And the plot looks something about like this. We have a flat portion right here at MP. We have a linear region between MP and MR, and then we get this hyperbolic region that looks like this. Okay? This, if you want an explanation as to what's going on, this is the elastic range. This is the inelastic range. And this is fully plastic. Now, where does everything else come into play? Okay, these 2 points, this right here, this is LP, okay? This is LR, okay? All right? Look right here. Change in Y over change in X. This line is at a given slope, right? I propose to you that the slope of that line is that beam factor. That's what that was, okay? Does that make sense? Kind of clears up a little bit. So the first thing we needed to figure out is, were we in this range, or this range? Okay? In design mode, you never really want to be in elastic range, which is why the manual doesn't even give you the formula for the elastic range. It's either that or this. And if it's this, the capacity is just MP, and you look it up, and that's all there is to it. Okay? Now, a couple other points. Going back to this table. Okay, this is called the ZX table for a very special reason. If you look, they're organized in terms of ZX values. See how the ZX keep descending? All right. See how they're broken up into these chunks? Like, here we got 6 shapes, here we got 5 shapes, whatever. And notice how the top row is always bolded. See that? Why is the top row bolded within this group? I want you to pay attention to this group right here. What's special about the top shape versus all the others? It's the lightest, right? This is a W21 by 55, 55 pounds per foot. This costs less money than the W12 by, say, 79, 79 pounds per foot. Make sense? Okay. Keep that in mind, the bold shape. All right? I then want to look at this. Okay? Now, I know this looks like a damn mess, but remember that LTB curve I showed you? This is basically all the LTB curves all plotted on top of one another, all at the same place. It actually is a very good idea. Notice how some of the lines are dashed, some of the lines are solid. What's true about the solid lines? Exactly. Exactly. In design mode, what you would do is you would say, this is what you would do. You would say, all right, let's say I have an unbraced length of 12 feet and I have a moment of 330. I would find that point, go this way. Whatever my first solid line is, that's my design. So it really is a very useful aid. Now, if you remember, we were dealing with what, a W24 by 55? Because in other ranges, they might not be so dashed. You see what I mean? And it's nice to have them because in the real world, what if a particular shape isn't available? All right?
Why are the groups so it's like one of the groups is just one shape?
That's a good question, and there's a couple reasons for that. Number one, they have purposefully deleted some shapes out of these tables for a very specific reason. And I don't want to get too heavy into the steel design, but I'll say this. Okay, All this whole time I've been talking about buckling. I've been talking about an idea called global buckling. In other words, the whole beam buckling. Make sense? What if the whole beam doesn't buckle? What if it's just the flange that buckles? The little plate, what if it buckles? Or just the web? Okay? Well, no, it's not a matter of being screwed. It's a matter of now it's a whole different set of calculations. Okay? So to keep it simple, a lot of those shapes have not been provided. That's number one. Number two, just because the way we manufacture rolled shapes, there's no nice, simple, okay, every 6 shapes will be the most economical. Sometimes there's groups of 6, sometimes there's groups of 15. It sort of is what it is. I don't really know that there's a better answer than that without getting crazy into the steel design. Is that okay? Okay. All right. Reason why I wanted to go back to this curve, if you remember, we're dealing with what, a W24 by 55? If you trace, what, 12 feet, and you take that 12 feet, let me do this. If you take that 12 feet and you trace it all the way up, was it a W24 by 55? We're about right here. Does everybody see that? And what's the capacity? And isn't that what we calculated? We got what, 342, 342. So this is 330, 333, 336, 339, 342. Assuming, so that's a quick way of doing it, if you can see it. Now you might wonder, well, how come that isn't solid? It was solid in the table. How come it isn't solid here? And it's all because in different unbraced lengths, that might not be the most economical shape. There's no real simple answer. The LTB curves, in different ranges, certain shapes are more economical than others. There's really no other way of saying it than that. So, any other questions? All right. Let me see something real quick. I have here, if you would like, we can go through this. I have here a tension member problem. It's a little involved, and one thing I will say about tension members, I would not expect them on the exam as readily as I would a beam or a column. If you go into the manual, most of the steel stuff in the manual is for beam design and column design. Tension members are an afterthought. Tension members are the first thing that we do when we take steel design, but they're really the least common structural element by and large. We do them first because they serve as our introduction to how do we use the manual, how do we understand a specification. The calculations are really simple. They're arguably the simplest of everything that we do in the class. I leave it totally up to you. Do you want to go through this example or not? We can go through it. We can take it off. We can just call it. You tell me. It's up to you. Want to go through it? It's not okay. Let's just knock it out. Let's just knock. 16 minutes. Let's see if I can do it in 16 minutes. Okay. All right. So we have an angle. So this angle is 6 by 4 by 3/8. So the 6 by 4 means one leg is 6 inches, one leg is 4 inches. The 3/8 indicates how thick the plates are. So it's grade A36 steel. So if you took steel design, you should remember that the FY, the yield stress, is 36 KSI, and the ultimate tensile stress is 58, 36 and 58. All right. Now, this might be a little tough to see on the screen. I don't know how well it showed up on your handout. Let me see. How did that show up on your handout? It's pretty reasonable. So we've got a bolt here, bolt here, bolt here, bolt here, bolt here. We've got 3/4 inch diameter bolts. They're staggered. Why would you ever stagger a connection? It ultimately has the opportunity to increase your cross-sectional area. because, you know, if I'm yanking on this, this angle, it may fail like this, you know, right through, you know, laterally, or it might fail like that. And failing along that diagonal path increases the cross-sectional area. And we handle that by using what's called a stagger factor. And you'll see that here in a second. All right, we have 5 bolts that are 3/4 inches in diameter. What is most nearly the design axial capacity? There are really 3 tension member limit states we need to check when we do this type of problem. One of them is looking at the yielding capacity of the member. One of them is looking at the fracture capacity. Now the other is block shear, but you can see block shear is being neglected. Block shear is assuming that a chunk of that connection material is going to rip out. And that's really not, I don't want to say that you shouldn't expect that, but I think the probability of that being on the exam is really low. Okay? Now, for this problem, because it's an angle, you had to be given some additional properties. One of these properties is the gross area. You know, cutting a section, what is the area of that angle? You had to be given that. And you had to be given a centroidal distance. You need that for a shear lag factor that you'll see here in a second. Okay? Now, going to the manual, let me go to this. If I look at the capacity, I have 2, if I ignore block shear, I have 2 capacities that I need to check. The capacity of the member in yielding and the capacity of the member in fracture. Okay? So let's take each of these one at a time. Now the yielding capacity is really simple. Okay? Yielding capacity is really simple. So problem 6. So for yielding, the phi-pn, or phi, it says Tn because it's tensile capacity, it doesn't matter, is 0.9, because that's phi is 0.9, Fy Ag. So that's 0.9 times 36 KSI times what? What's Ag? 3.61? And what is that? Okay. Now that was a really simple calculation, wasn't it? Now, here's what's going to happen before we move any further. Okay? Here's the yielding capacity. We're going to calculate a fracture capacity here in a second. Okay? Now, whatever value we get, the lowest value is going to govern. In other words, if I take this angle and I'm yanking on it, I'm trying to figure out how it's going to fail. Okay? It's either going to fail by yielding first or by fracture first. And I determine that based on the lowest capacity. Does that make sense? Okay. Now I want you to look at the A, B, C, and D. Okay? One of 2 things is going to happen when I calculate this fracture capacity. I'm either going to get a smaller number, and the design capacity of this member is going to be that, or I'm going to get a larger number. If I get a larger number, then the design capacity is 117. If that's the case, if either of those 2 are the case, is there a choice I can eliminate right now? It can't be D right off the bat. It's very possible that it could be C though, right? We don't know if that's the case. Make sense? Right off the bat, D's gone. Okay. Now, for fracture, the design capacity is 0.75 times FU times AE. Goodness. Yes, you know. I know. All right. Now this AE, this A sub E, is an effective net area, okay? And I calculate that by saying 0.75 F sub U times A, oh goodness. Never gets old, never gets old. The effective net area, I calculate that by taking the net area and multiplying it by this value U. I'm going to explain what each of those are here in a second, okay? So far, so good? So once we get the net area and once we get U, we're golden.
So the U's not in the, under this,
Look on the next column. Yeah. Do you see it over there? Well, when you've had the class, this is, I mean, I'm doing my best to review based on if you haven't had the class. So I'm trying to cover the broad strokes. Okay, let's deal with each of these one at a time. So net area. What is the difference between net area and gross area? So, what's that? The bowl holes, exactly. So if I cut through the main body of the angle, we call that the gross section, the main area of the tension member. The net section is right there around the connection. And in general, the net area is equal to the gross area minus the area lost due to bolt holes. Does that make sense? Now, if I go back to my PowerPoint, there's two possible fracture paths, okay? One of them is just, perpendicular straight through the section. So how many bolts am I going through on this blue path? One. How many through the second path? Two. So here's the difference. My first path, I'm only subtracting through one bolt. The second one, I've got two bolts, but I have to add a stagger factor. And we'll see what that is here in a second. Okay. So I want you to look here over that left-hand column, okay, and we'll see how this goes. Okay, net area. Okay, my first path, I propose that the net area is going to be the gross area minus one bolt hole, okay? Now, how do I get that? I take the diameter of the bolt and I add 1/8 of an inch, and then I multiply that times the thickness. Now, first off, how am I just getting that formula? Well, if I have a plate, and here's the plate, and I'm yanking on that plate with some load, right? And I've got, a bolt hole here, and then I cut through that. That's what I'm cutting through, right? That's what I'm going to see. So what's the area of that shaded rectangle? Well, it's the diameter times the thickness. Make sense? Now, that 1/8 of an inch comes from two things. Number one, if you've ever done any mechanic work or anything like that, you cannot take a 1/2 inch diameter bolt and try and fasten it through a 1/2 inch diameter hole. It doesn't work like that. The hole needs to be slightly larger. Okay? Standard bolt holes are a 1/16 of an inch larger. So there's 1/16. Another 1/16 comes from the damaged material right there around the plate that you get from drilling or punching or, that hole or what have you. We just say, well, we really can't count on that. So we're adding 1/8, but it really means we're kind of adding a 1/16 twice. 1/16 plus 1/16. Make sense? Okay. Well, if you look at that, that's what I was mentioning earlier. If you look at the formula, it says that the net area for parallel holes is the sum of the diameter of the hole plus a 1/16. But then look at the very top, the diameter of a hole is the diameter of a bolt plus a 1/16. So I think that's misleading, personally. I think they should just collapse it, but that's me. So this is going to be 3.61 square inches plus, we have what, 3/4 inch diameter bolts? So 3/4 plus 1/8, that's 7/8 of an inch times the thickness, and the thickness is what? What's the thickness of that angle? 6 by 4 by 3/8. And what do we get here? What'd you say it is? 4.86 square inches. So far, so good? Now, that's the first possible failure path. Oh, I'm sorry. That's my fault. That is supposed to be minus. Sorry. You're subtracting a bolt hole. I was thinking too far ahead.
That's not right. Yeah. 3.28.
3.28. Okay. All right. So far, so good? Okay. I might have a future typo here. We'll see how that works. But it'll be all right. Okay, so there's that. So that's the first path. Now the second path, what I propose is that the net area is going to be the gross area minus 2 of those bolt holes plus a stagger factor. And we're adding a stagger factor because we're recognizing that that diagonal path, we're going to get increased area. So I propose that that is s squared times t over 4g. Okay? Now, are you all seeing where I'm getting that in the manual? Y'all see that? Okay. Now, so everybody's aware, the G is how far apart the bolts are spaced this way. You know, you're yanking on it like that. So G is going to be 3 inches. The S is how far apart they're spaced this way along a diagonal path, and that is 1.5. All right? Does everybody see that? Okay. So that is 3.61 minus 2 times 7/8 of an inch times 3/8 of an inch plus 1.5 inches squared times 3/8. Oh, what the heck? Over 4g, and that equals what? $3.02. Okay. There might be a typo in the question. We'll just see. I'll take your word for it. All right. So far, so good? We'll just see what happens. Okay. Now let's deal with this U factor. Okay. Now this U factor deals with a phenomenon known as shear lag. And I'm going to do my very best to explain that quickly. Okay. Let's say you've got a creek, and the creek doesn't have any rocks in it. It's very uniform, very perfectly even depth, and it's flowing. It's going to be a nice, steady flow, right? Now let's say I take that creek, and let's say I throw a big boulder right in the middle of the creek. What's going to happen? The water's going to go all over the place, right? Make sense? Now, the water's going to go all over the place right there where that boulder is. A couple hundred feet down the way, it's going to be like that boulder wasn't even there, and the water's going to go back to being very calm and serene. Make sense? Okay. I propose that bolts in a tension member are like boulders in a pristine creek. You throw a bolt into an angle or what have you, they take the stress field and disturb it all over the place. You look at the stresses right there around the connection, they're a mess. Now, away from the connection in the gross section, the stresses go back to being uniform. But when we calculate fracture capacity, we're not looking at the gross section. We're looking right there where those bolts are. See, some of the angle is going to experience a lot of stress. The rest of it isn't experiencing all that load, and it's kind of lagging behind. So we calculate a shear lag factor to adjust that area for that effect. Does that make sense? That's kind of what's going on here, and that's what this shear lag factor is. Now, to calculate shear lag for a situation like this, it's going to be 1 minus x bar over L. Now, x bar was given, that's 1 minus what is that? 0.933. The L is the total out-to-out length of the connection. Okay? So when I say out-to-out length of the connection, I mean from bolt to bolt. So how far is that? Think about that. Well, think about it like this. That 5 at 1.5 inches, we've got 1, 2, 3, 4. So, here's our spaces. I got space here, space here, space here, space here, and space here. See, I'm getting the 5 at 1.5? Okay. Now, I propose that the length of the connection is sort of from here to here, the out-to-out length. And what is that? 6 inches. Make sense? Is everybody okay with this? You got a perplexed look on your face. I could spend a long time talking about the behavior, and I don't have a terrible amount of time on that. This is another one of those empirical expressions, kind of like the square root of FC prime.
For some reason, I was thinking it was 5 inches.
No, it's 5 at 1.5.
Yeah.
All right. This problem is almost done. Okay, I promise it's almost done. All right. So this is 6 inches. What does that come out to be? Say it again. 0.845. Okay. So now we can calculate the fracture capacity as is 0.75 FU net area times U, and that's 0.75 times 58 KSI. We have net area of, which net area? I didn't even mention that. The smaller one, exactly, the worst case scenario. So that's 3.02 square inches times the shear lag factor of 0.845, and that equals what? Say it again. It actually came out to 111 again. Wow. What was it? 111 point what? 07? 0, okay, so 111. Everybody else get that? See, when I did mine, I had a typo, I think. What it was is I think I was looking ahead. I think I used 0.943 as my shear lag factor, and my numbers came out a little differently. I also, for some reason, I had a different connection length. I think I adjusted the problem later. But ultimately, here's the long and short of it. So here's your capacity according to fracture. Here's your capacity according to yielding. So really, the actual capacity of this section, the VPN, would be 111. Now, when I did the problem, I got that the fracture capacity was a lot higher, so the answer ended up being the 116. So I apologize for any confusion there, but that's actually the answer. So you'd pick the one that's nearest to that. So I apologize for that. You'd pick the smallest, so that would be your answer. Because think, if I take this angle and I pull it, I'm going to reach that load before I reach the other one. No.
I mean, it's the right answer still, but it's not
Yeah.
on purpose.
Yeah, exactly. Yeah, it's actually, C is the right answer, but what was supposed to happen is the fracture capacity was supposed to come out to be 124, and then that would have been your answer. So, whoops. But actually, just by osmosis, that ended up being the answer anyways, which that can happen. You can have answers, actually on purpose that are a little bit off. One of the things about the exam, they use most nearly a lot to try and eliminate any potential errors that might be because of rounding. Like if you two do the problem exactly right, but you round differently and get a different answer than him. They try and avoid that. So, any questions? All right. Hopefully this helped. I'll be around if you all have any questions, but that's all I've got.